All right, here's some basic derivative review. You can find this in the modules. There's a new module for AP review. And this is just like, what is a derivative? Most basic stuff. After watching this video, I hope that you will be able to complete a task on the AP Classroom, a mock FRQ. Okay, my graphs did not come out. Oh my goodness, because my ink cartridge is super duper low. So I'm going to be playing along with my whiteboard that I brought as well. So here you are. The very first thing that we did with derivatives is find an average rate of change, which is a slope. And if it said over, then that wasn't calculus. This was algebra. And so if I want to find the slope from 2 to 4 on the parabola, you really just played algebra 1. So I have this pre-graphed for you. And if you want to find the slope from 2 to 4, then you really want to find the slope of this line, which we call the secant line. And you're just going to use the same formula you've been using since algebra 1. You're going to go ahead and do the change in the y's over the change in the x's. When you do the change in the y's over the change in the x's, you would get f of 4 minus f of 2 over 4 minus 2. This one, if you go ahead and figure it out, I believe that f of 4 is 6, f of 2 is 0, and so we are going to get 3. That means the slope of that secant line that I just drew, the slope of this secant line is 3. The algebra 1 slope is 3. Where it started to get into calculus is instead of saying an average rate of change, we changed the word average to instantaneous. This is now your slope, but it's a calculus slope. It's the slope at a point. If you see the word at, you need to use calculus. So we did the problem at first using limits, and you do not ever have to do this again, but the College Board does want you to recognize that these are the old school ways to find, really the formal way to find a derivative. So this is like where we traveled h and we shrunk h and we were right up on the point. Or we moved away from 2 and then came back to 2. Both of these are ways that we used to find slope at a point. Instead of doing this, just know if you see these, that this is asking you for the derivative at 2 in this case. So what we're going to be asked to do this time is on the same exact parabola, we want to find the instantaneous slope at 2. And that would look like this. The slope of the tangent line is the slope at the point, and we learned a bunch of rules to find it very quickly. If we have the function, we could just find the derivative, and then you use the derivative to spit out your slopes. So the slope at 2 is 2 times 2 minus 3, that's 1. So the slope at 2 is 1. If you go back to my picture, what I'm saying is that the slope of this tangent line, the instantaneous rate of change, is 1. So when we first learned about derivatives, we went from the average rate of change over an interval, which was your algebra slope, to the instantaneous rate of change, which was your calculus slope. Let's fill in this chart to really get this point across. The average rate of change over an interval is your slope of a secant line, and that's just an algebra slope. You literally use your change of y's over change of x's, y2, y1, x2, x1 formula from way back when. Instantaneous rate of change, and look for the word at, is your tangent line, and the slope of the tangent line is the slope of the function at a point. This is a calculus slope, and we use derivatives to find this. Okay. So the most important concept we learned fall semester is that the slope at the point, which is the slope of the tangent line, which is the instantaneous rate of change, is called, I have no idea if it's on this other sheet, but if it's not, it's the derivative. Okay, good. Derivative. So derivative is a synonym for slope at a point. but it also is the name of the function that gives us all slopes. So going back to our example from before, which I should be able to quickly just sketch for you. Okay, so here's a parabola. So once we learned how to find derivatives, which this derivative is 2x minus 3, let's make the connection about the derivative being a slope spitter outer. So I'm going to go ahead and graph the derivative up 2 over 1, up 2 over 1, up 2 over 1. And the way that this works is that these y coordinates tell me about the slopes on this original function. If I want to know the slope on the parabola at 1.5, so let's go ahead and look at the parabola. Let's look at 1.5 and let's guess that the slope is probably going to be 0. And then you go over to the derivative, and at 1.5, the y coordinate is 0. The y coordinates on the derivative are the slopes on the function. If I want to know the slope on the parabola at 2, I'm guessing that it is a positive number. If I go to the derivative and I look at the y coordinate at 2, which is 1, that y coordinate on the derivative is the slope on the function. So now what's the slope at 3 on the parabola? Well, the y coordinate at 3 is, why can't I see that? 3. What's the slope at 0 on the original function? I would guess that it's a negative value based on its tangent line. Let's go ahead and look at what the y coordinate is at 0. So the y coordinates on the derivative are the slopes on the original function. Okay, I just drew in the function since my ink cartridge did not work. It did not deliver. And here's just a couple more functions to really deliver that point home. If this is your original function and you want to know what the slopes are at all of these places, then on the derivative function, these y coordinates are the slopes on the original graph. So the slopes are positive, the y coordinates are positive. In fact, the slopes are positive over here as well, and the y coordinates are positive over here as well. If you zoom into the cubic, it has a horizontal tangent, and sure enough, the y coordinate is 0. Looking over here at an absolute value graph, these slopes are a constant negative. These y coordinates are a constant negative. These slopes are a constant positive. These y coordinates are a constant positive. The y coordinates on the derivative correspond with the slopes on the function. I drew something with a corner on purpose because I wanted to also remind you in our basic derivative review about the fact that sometimes there is no derivative. So that brings us to differentiability. There is usually always a derivative, but there isn't a derivative or the function isn't differentiable if you can't draw a tangent line there. So if there's a hole, there's no derivative. If there's a cusp or a corner, there's no derivative. And there also wasn't a derivative if you were able to draw the tangent line, but the tangent itself was vertical. The reasons that you would write for the College Board: vertical tangent, one-sided derivatives differ, or left and right hand derivatives differ. And in fact, I think you're going to need this for the first problem that I assigned from the College Board site. And this one here, the function is discontinuous or fails to be continuous. Continuing with basic derivative review, our earliest rules, a couple of which you'll need for the College Board problem that I'm assigning, are power, product, quotient, and chain. So power rule, you move the power down, you subtract 1 from the power. I just wanted you to hear my voice saying these things. I know you know them. For product rule, it's the first guy times derivative of the second guy plus the second guy times derivative of the first guy. For quotient rule, I'm going to abbreviate with H and J. we went ahead and did the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. And for the chain rule, we did the derivative of the outside, left the inside alone, and then did the derivative of the inside. What I'm going to do now is I'm going to start a second video where I take you through an FRQ type problem that tests this level of content. And then I've assigned one for you to do on the College Board website.